When a solution of an acid is mixed with a solution of a base, a neutralization reaction occurs. Neutralization reactions are reactions between hydrogen ions that arise from the acids and hydroxide ions that arise from the bases. Acids are said to be proton donors. They donate H+ ions to solution. Bases are said to be proton acceptors. They react with or accept protons to neutralize them to form the water molecule. Bases neutralize acids. We can actually say vice versa as well. Acids neutralize bases. In this chemical formula here, we've got H+ ions reacting with OH- ions. Now, we can't just have a source of H+ ions by itself. That's impossible. And we can't just have a source or a solution of OH- ions either. So the source of the H+ ions has to come from some form of acid. For example, hydrochloric acid. And the source of hydroxide ions has to come from some sort of base. For example, a solution of sodium hydroxide. So we can rewrite this chemical equation here. HCl, hydrochloric acid, plus NaOH, sodium hydroxide, react to produce sodium chloride and water. So what you see over here is molecular compound water being formed along with the aqueous salt here. So we've got a salt plus water being formed from the acid and the base. And this is a generalized reaction that's very, very important and one that we should remember. An acid plus a base will give you a salt plus water. So in general, we can write any acid down, react it with any base. We know that water will be a product, and then the trick is working out exactly what the salt is and what its chemical formula is. And then we need to be able to balance that equation, put appropriate subscripts in, and then if required, write a net ionic equation. The acid-base reactions are a double displacement metathesis reaction. In effect, the hydrogen from the acid is displacing sodium and it's combining with the hydroxide ion to form the water. At the same time, the chloride ion is displacing the hydroxide ion so that the sodium and the chloride ions get together to form the sodium chloride salt solution. So an acid plus a base gives you a salt plus water. Let's choose an acid, in this case the triprotic acid phosphoric acid. Let's choose a base, barium hydroxide. And this is actually the first step in writing out acid-base neutralization reactions. We write the chemical formulas of the reactant solutions in the form of a molecular equation. We know these solutions actually exist as ions, but we want to keep them in their molecular form, if you like, so that we know what two solutions are actually being mixed together. So the acid plus base gives me a salt plus water. So the step 2 here is assuming that the reactants actually react, write down the products based on a double displacement metathesis reaction. So what actually happens here is the hydrogens, we're going to swap anion and cation pairs, and the hydrogens from the acid get together with the hydroxides to effectively form the water, and the positive bit of the base, the barium, is going to get together with the negative bit of the acid, the phosphate, to form the salt barium phosphate. We need to make sure we've got the chemical formulas of these products correct, and at this moment neither of them are correct. If we look at this HOH over here, consists of a H+ ion and an OH- ion, but when they actually come together, they actually form the molecular compound water, as we've seen a little earlier. So we should replace that HOH with H2O. We're very familiar with that chemical formula. In terms of this barium phosphate, we've got to ask ourselves, is this the correct chemical formula for barium phosphate? Do barium ions and phosphate ions come together in a 1-to-1 ratio like this? Well, the barium ion is a 2+ ion because barium is a group 2 metal, and the phosphate ion is a 3- ion. So if we do our crisscross method here, we can take the 2 from the 2+ charge of the barium and put it down as the subscript for the phosphate ion. We can take our 3 from the 3- ion on the phosphate ion and put it down as the subscript for barium. And so the chemical formula for barium phosphate, Ba3PO4 and so we need to write that chemical formula in there now. So phosphoric acid plus barium hydroxide gives barium phosphate plus water. Acid plus base gives you salt plus water. We've written the chemical equations down correctly. Sorry, the chemical formulas down correctly in this equation, and now it's time to balance the equation. And remember, when we're balancing the equation, we only change the stoichiometric coefficients out the front. And because there's polyatomic ions involved in this, we want to keep polyatomic ions that exist on both sides of the equation intact. And here we can see we've got one phosphate ion on the left-hand side of the equation, and we've got 2 phosphate ions on the right-hand side of the equation. So we want to keep them intact and try and just balance the phosphate ions as a whole. You can see we've only got 1 barium atom on the left-hand side, and we've got 3 barium atoms on the right-hand side. You can see that we've got 3 plus 2 hydrogen atoms on the left-hand side, and we've only got 2 hydrogen atoms on the right-hand side. We've got 2 oxygen atoms on the left-hand side, that's excluding the oxygens that are tied up in the phosphate, and we've only got 1 oxygen atom on the right-hand side, again excluding the oxygens tied up in the phosphate ion. So clearly this equation needs balancing. We've had lots of practice with that, and if we put a 2 in front of the phosphoric acid, a 3 in front of the barium hydroxide, and a 6 in front of the water, we'll see that we've now got a balanced chemical equation, same number of atoms on both sides of the equation. What we do now is we use our solubility rules to determine if any products will form insoluble salts. So we need to assign either an AQ subscript or a solid subscript, or maybe even a liquid subscript or a gas subscript if liquids have been produced or if gases have been produced. In this case, what we've got is the molecular compound H2O, or water, being formed, and that is a liquid. It's not aqueous, it's not a solid, it's not a gas at room temperature. We don't refer to water being produced as aqueous water. Water is actually the solvent, it's a liquid. So we're going to put the L subscript next to H2O. Then we've got to look at barium phosphate. Is barium phosphate a soluble salt and therefore will have the AQ subscript, or will it form a solid precipitate and therefore have the S subscript? Well, to answer this, we go to our solubility tables. We look up our solubility rules for phosphate, and we can see here that most phosphates are insoluble, and the only exceptions being the group 1 metal phosphates or ammonium phosphate. Barium does not fall under that category, so barium phosphate will form a solid precipitate, and we are going to put the S subscript there. So step 5, if we need to write out the net ionic equation, then let's write out the full ionic equation where all the strong electrolytes are written as individual ions, and then we're going to identify spectator ions and we're going to cancel them out to get the net ionic equation. So here's the full molecular equation that we've just balanced. We can write out the full ionic equation here where all the strong electrolytes are written as their ions individually solvated and floating around in solution. For example, we've got the 2 lots of phosphoric acid. There's a total of 6 H+ ions associated with that strong electrolyte and 2 phosphate ions associated with that strong electrolyte. In the 3 barium hydroxide, there's 3 barium ions floating around in solution and a total of 6 hydroxide ions floating around in solution. The barium phosphate solid is not a strong electrolyte. It doesn't dissolve in water, and so we are going to keep the barium phosphate solid written as Ba3PO4 2S. And then we've got our 6 waters, which is again not a strong electrolyte. It has the L subscript, so the water is just going to be written as 6H2O with the L subscript there. So what we need to recognize here is that the 6H plus ions and the 6OH minus ions on the left hand side of the arrow are actually combining to form these 6 waters. So clearly the H plus ions and the hydroxide ions have undergone a physical or a chemical change, in this case a chemical change. The other thing we need to appreciate is the 3 barium ions on the left hand side and the 2 phosphate ions are actually coming together to form the solid barium phosphate. So again, these ions have undergone a physical change, going from the left hand side of the arrow to the right hand side of the arrow. There are no spectator ions here. Everything on the left hand side of the arrow has undergone a physical or a chemical change to get to the right hand side of the arrow. There are no spectator ions to cancel out, so the net ionic equation in this particular example is identical to the full ionic equation. So in summary, predicting the products of acid-base reactions. Step 1, write the formulas of the reactant solutions in the form of a molecular equation so that we can identify the 2 solutions that are being mixed together, one acid, one base. We assume the reactants actually react. We write down the products based on a metathesis double displacement reaction, and the salt that we identify, acid plus base gives you salt plus water. The salt that we're identifying takes the cation of the base with the anion of the acid. We balance the equation. We use the solubility rules to determine if any of the products will form insoluble salts, and then if applicable we take the full molecular equation, write out the full ionic equation, cancel out any spectator ions to get to the net ionic equation.